right. Well, good morning, good afternoon, everyone, and welcome to today's Exploring by the Seat of Your Pants event. My name is Joe Grabowski, and I'll be your host for today. October is always a great month. It's always a time that we dedicate a lot of our live events to space exploration. So, of course, we talk to astronauts who leave our planet, but we love to bring in as many engineers and scientists as we can because they're the ones who are really working hard behind the scenes, crunching those numbers, building exciting new technologies, and making all of these missions happen, and then pushing well beyond our planet to explore our solar system, out into the universe, and then, of course, to turn a lens back and help us understand our planet better. So lots of events still to come this month. If you take a little trip to exploringbytheseat.com, you can find all of the events we have coming up, not just space exploration, but a whole variety from the world of science, exploration, adventure, and conservation. So take a minute, register for some of those events, tune in live in camera spots or via YouTube. Lots of ways you can join the action. All right. Well, joining us today, we have Ravi Prakash joining us. He joined NASA's Jet Propulsion Laboratory in 2005 and was part of the team that landed the Curiosity rover on Mars. He took a break from JPL to design products to help lift people out of poverty, but has since returned, where he has been on all kinds of incredible projects, like leading the operations of the InSight lander on Mars. He helped integrate science instruments for the Psyche mission to visit an asteroid, and he's now managing a group that designs hardware to land spacecraft on different planets. So I'm going to bring Ravi in live with us right now. Hey, Ravi, how are we doing?
Good. How are you? Thanks for having me.
Good. Well, it is great to have you with us. You are a veteran of live space exploration events with Exploring by the Seat of Your Pants, and it's always great to get to catch up on all the exciting stuff you're working on.
Yeah, thanks. I'd love to talk about it.
All right. Well, I'm going to let you take over for a bit, and then we'll turn the classrooms loose.
Sounds good. Okay. I have a few things I want to share, but first I want to tell you where I am. So I am in NASA's Jet Propulsion Laboratory, and I'm in mission control. So this is a place where whenever we do really cool things like land on Mars or go around a planet, a lot of the engineers are in this room looking at the data live as it comes in from the spacecraft to see how that event went. And I'll talk more about that in a little bit. But for now, let me give you an overview of the work that we do here. And so I'm going to share my screen. Okay, so I'll be talking a little bit about a special project we're doing, which is, going to Mars, getting dirt, and bringing it back to Earth. And I'll talk about why we're doing it and why it's so important. And I'll tell you a little bit more about JPL first. So JPL stands for Jet Propulsion Laboratory. We are one of 10 NASA centers spread across the United States. We are located in Northeast Los Angeles in a place called Pasadena, California. And there's a lot of people that work here. There's over 6,000 people working on hundreds of projects that make all these missions happen. What's really cool is that we focus on robotic exploration of space. So while a lot of the other NASA centers are focused on how do we get humans to the moon, let's get astronauts to the space station, we focus on robots. And that means that we can take more risks. We can go further than we can with people. We've been to every planet in our solar system and beyond, whether we've landed on a planet, orbited the planet, or flown by and taken pictures, the very first pictures of planets. JPL landed America's first spacecraft on the moon before there were people. We sent robots to understand what would it be like to land on the moon. We've flown by the sun and understood why is our sun the way it is. We did the first seismometer on Mars to understand, are there Mars quakes? Just like we have earthquakes on Earth, are there Mars quakes? How did Mars form? And we've done many, many other firsts. America's first satellite into space was from JPL. And so it's a really cool place to work. We're trying to understand the biggest questions like, is there life beyond Earth? And that's the kind of stuff we get to do every day. How many places get to say, we're trying to understand, is there life outside of Earth? So it's a really, really fun place with a lot of excited people that get to work here. So the project I'll be talking about, I'm going to start talking about the mission that went to Mars about 1.5 years ago called Mars Perseverance. And this is the first leg in a multi-project campaign that's going to bring dirt back from Mars. So I'll start with this animation. This animation shows us about 1.5 years ago how we landed on Mars. So we had this capsule that's bigger than the capsule that landed the Apollo astronauts on the moon. And we have to slow this thing down, going from 5 times as fast as a bullet all the way to 0. And so we deploy this huge parachute, which is 7 stories tall. Imagine a really big parachute. We have this rover attached to a rocket backpack that we throw out of the capsule. We light the rockets, and it's slowing down. It's screaming to a halt, looking for a really good place to land. It says, all right, there's a good place. Let me lower this rover down on some ropes. When the rover tells me I'm safe, I'm going to cut the ropes, push that rocket backpack far away so when it crashes, it won't explode on the rover. And then I'm going to start my mission. Isn't that really cool? Like, that's such a crazy way to land. But some people thought about, hey, how can we land in a way that's safe and will meet all our requirements and get this rover going on its mission? And so that's what we came up with. We were crazy enough to try it out, and it worked. Now, another part of this mission that a lot of people don't know about is that there's a helicopter on this mission. So there's a helicopter on Mars right now. And this is something that we called a technology demonstrator. So we weren't sure if this mission was if this helicopter could fly. The air on Mars is really, really thin. So if you flap your arms around, and you'll feel the air around you. The air on Mars is 100 times thinner than the air on Earth. And so if you flapped your arms around on Mars, you would hardly feel anything, if at all. And so a lot of people said, well, you can't fly on Mars because the air is so thin. And so we had a lot of women and men who said, you know what? I bet we could try it out. Because if we don't try, we're not going to know. So they built a really lightweight helicopter. We did a lot of testing on Earth, the best we could, to understand, would it fly on Mars? Maybe, maybe not. But then we took it to Mars, and we tried it out. And this is just an animation, but I'm going to show you a video now of this thing actually flying. And we were both surprised and excited and just delighted that it flew so well. So what you're seeing on the right-hand side is the helicopter went up, is taking pictures of its shadow on the ground, and it's flying. And this was flight number 9. It happened about a year ago. It was July 5th last year. And it flew, almost 700 yards. So it flew like almost 7 football fields worth. And this is a very lightweight helicopter, really small battery, solar powered. And it did an amazing job. And so now we know that we can fly helicopters on Mars. And the reason this is really cool for us is because the rover, when we have the rover on Mars, it's sitting there and we're thinking, okay, which way should we go? But with a helicopter, we can sort of send it out as a scout and say, hey, let's look all around where the rover is and find the most interesting area for us to explore. And then I'll go back and report to the team on Earth and say, hey, here's all these pictures. You all make the decision. The people will say, yeah, this place looks really interesting. Let's send the rover over there. And so it's a much more efficient way of using our rover on Mars. What's also super cool is that if you remember that animation, we had part of the capsule and the parachute. The bottom part fell off so we could throw out the rover. Well, the helicopter found the back shell, which is what we call the back shell, the back part of the capsule, and the parachute. And so it flew over there and took some pictures for us. And this is really kind of the first time we've had this kind of picture from Mars of the stuff that helped us land on Mars. It turns out, on the Mars exploration rover missions, they actually drove up to the heat shield, the part that's on the bottom. But this is the first time we've gotten pictures like this of our parachute in the back part of the capsule. So it's really cool. We have engineers right now that are looking at this information, looking at this data, and saying, oh, like maybe I can reconstruct what kind of happened on its way down, or how hot did it get? Things like that. So back to the rover. So this rover, Perseverance, is on Mars right now. And one of the main objectives of this rover is to put dirt into tubes. And the reason that's cool is because it's going to put dirt into tubes so the next mission can grab that dirt and send it back to Earth so our scientists can look at it and tell us a lot more about Mars than we know today. And so right now, this rover has putting dirt in a lot of tubes. It's about to put a lot of those tubes on the ground, which is those tubes that you see on the ground in this picture here. This is an artist rendition. And it's going to keep a bunch of tubes on the rover itself. And the reason it's going to do that, this is sort of the suite of spacecraft that's required to bring dirt back from Mars. So this is the rover we've been talking about. This is the next thing we're landing on Mars. This is a beast. It is so huge. It's bigger than our rover. It's going to be harder to land. It's much heavier. Every pound we try to land on Mars it's harder for each additional pound. It's just heavier, and it takes maybe a bigger parachute, a bigger capsule, everything. Everything becomes harder about that problem. And so we're landing this beast on Mars. And you see this flat part here on the top of this lander. By the way, it's called a lander, not a rover, because it only has legs. It doesn't have wheels. So once it lands, it's stationary. It's going to stay put. It has this flat part here. And on this flat part is going to be this rocket. So we'll have this rocket laying down here. When this lands, the plan is, if Perseverance is still alive and well and driving, it's going to drive over to this lander. The lander has this robotic arm. It's going to grab those tubes of dirt, put it on this part of the rocket, and then that rocket would launch. If the rover, let's say the rover isn't alive and well, because it wasn't meant to last that long. We now know that helicopters can fly on Mars, right? Super cool. So we're actually also going to put two small helicopters on this thing. That's our current plan. And they can fly over to where the rover dumped those tubes. They can fly over and say, hey, let me grab these tubes of dirt and bring them back to the lander. Then the lander's robotic arm will grab those tubes, put them in the rocket, and the rocket would launch. So we have two different ways of getting these samples when we land our next mission, which is really, really cool. Now, I mentioned this rocket is going to be laying down flat. But on Earth, we don't launch rockets flat, do we? We launch them straight up and down. So you might think, oh, well, let's just raise it up, have it go straight up and down, and launch it. But there's problems with that. We don't want all that heat and everything spewing into the lander. Maybe the lander would crumble. It'd have to be a much beefier lander, which means even heavier. There's lots of different problems. So we had some engineers come up with a really clever way that we think we're going to do, which is maybe we just throw this rocket up. So we're going to throw it up to where it's tilted. And then while it's in the air, it's going to ignite and then go all the way up to this orbiter that's going to launch to Mars as well. This is another spacecraft we're building for getting dirt back from Mars. And this little part up here, it's going to rendezvous, which is a fancy word for it's going to meet up with this orbiter. And then this orbiter is going to shoot it towards Earth. And then it's going to land in Utah, in a desert in Utah, in the United States. And scientists will grab that dirt. They'll put it in a lab and use really sophisticated instruments to help understand what Mars is made out of. What is that dirt made out of? And we'll have dirt from different parts that this rover got. One more thing I'll mention about this is that you'll notice this helicopter looks a little different than maybe the one that I showed in the video. That animation, that helicopter didn't have wheels, but this one has wheels. The reason this one has wheels is because it has to get these tubes. But if we wanted to land let's just say we wanted to hover and grab a tube and then fly back, it would have to have a lot of precision, a lot of accuracy to figure out where exactly that tube is and just hover right over it, which maybe it would have to be a heavier helicopter to do that. We could do it. It would just have to be bigger and heavier. And we already know the air on Mars is really, really thin, so it has to be a light helicopter. So what if instead we just had to get close enough to these tubes, then it can drive over slowly using human input, or maybe artificial intelligence, grab those tubes, fly back to this lander, land near it, and drive to the lander, and then the lander would grab those tubes and put it back on. So it's sort of another creative way of, let's just make it simple for us, because simple means less things can happen wrong. And maybe it's cheaper, maybe it's lighter. There's a lot of advantages of being simple. And yeah, we'll try that out. So this is the cool mission that a lot of people at JPL are working on, in addition to many, many other missions that are happening right now. We're going to Europa. We're going to asteroids. We're going to a lot of other places, Venus, other planets, where many, many exciting things are happening. Here's sort of what we call a family portrait of the rovers on Mars. It's probably even hard to see this one on the very left, which is the Sojourner Rover, which was from the 90s. And it's so small. It's about the size of a wheel of the rover that we have on Mars right now. And that was followed by Spirit and Opportunity rovers, which are the next two. They were twin rovers put on opposite sides of the planet, followed by the Curiosity rover, which is the first car-sized rover. So, the first one was the size of a tire. The second two were the size of maybe like your school desk. Then you have the Curiosity rover, which is the size of a car. And so that's when we used this, that animation you saw of how we landed on Mars. We did something very similar for Curiosity. Then the Perseverance rover with the helicopter. And then, this thing that we're designing right now, which it's still, the way it's going to look like is still being figured out. All the way which we're going to do things are still being figured out. But eventually the goal is to send people. Because, you could send all the robots you want, but a person on Mars, after a few weeks, would have learned more than all these other missions combined, because you can't replicate the human brain in a robot, at least not yet. There's so much that a human can just figure out. There's so much distance they can cover, and you could just send so much more with a human than you can with a robot. And so, who knows? It will happen in your lifetime that people will go to Mars, and maybe it'll be one of you. It'll probably be someone about your age that's going to be the first person on Mars. And that's really, really cool. And I'd love to end with this, which is, it takes a village to make these missions happen. People of all different shapes and sizes and colors and backgrounds. This is a picture of just a small percentage of some of the women that make our mission successful. Historically, engineering was a very male-dominated field, and still in many ways, we're still making progress to have it be a more diverse field. But if you are a minority or someone that's underrepresented, or maybe you're in the majority and an ally, it's always good to make sure that your teams are very diverse, because the more different backgrounds people have, the better the ideas. If everyone came from the same sort of background or the same school or anything, you would all have the same sort of ideas. The way we have successful missions and the way we get creativity is to have people of all different backgrounds sharing their ideas from their different life experiences. And that's what makes our mission successful. And so if you ever feel like maybe you're the only woman in a room, or maybe you're the only whatever in a room, your voice matters because you have a different experience than everybody else. And so don't be afraid to chime in with an idea or why you think that something should be done a certain way. And that's this part of it. I would love to take all the questions that you all have.
All right. Awesome. Well, Ravi, thank you so much for another incredible presentation. I hadn't seen that photo before where the helicopter found the back part and the parachute. That is so cool. That's awesome. Yeah. Great. Well, what we're going to do before we start meeting our classrooms is we're going to take part in a quick Kahoot quiz. So this is something we'd love to do to get students interacting. I'm going to share a little link here, kahoot.it. We'll see how well everybody was paying attention today. If you visit there, it is going to ask you for a PIN number. I'm going to share my screen right now, and we will get that PIN number up there. There we go. Play now. Okay, let's share the screen. There we go. Okay, so there's your PIN number, 9151498. If you're lucky enough to have one-to-one tech at your seat, then you can join right there. If your class doesn't have that, that's no problem. Your teacher can pop it up on the board and you can shout out your answers. If you're using a tablet or a phone, sometimes it's quicker just to scan that QR code up at the top. That will bring you in. I see our auto-generated animal names joining already, like the awesome gecko and the soaring seal. Very cool. There will be 4 questions, some true and false, some multiple choice. You have 20 seconds to get your answer in. You'll get a point if it's right. You will get more points if you do it really quickly. If you do it as fast as you can, but it's wrong, well, we got nothing for you. So you got to get that right answer, and the quicker you're able to do it, the better it will go. And I see Kahoot has shifted to their Halloween theme in the background. Very cool. So we'll give another few moments here before we get to the Q&A. We've got great classrooms joining today. We've got classrooms in Canada and the US, of course. We also have classrooms joining us in Mexico and Portugal today. So we're looking forward to getting some of their questions when the time comes. Let's give it another 10 seconds and then we will launch. All right, here we go. Our first question, how many NASA centers are spread across the US? Was that 2, 6, 10, or 15? Got about another 10 seconds to get that answer in. How many NASA centers are spread across the US? All right, good job, crew. Most went with 10. That's absolutely right. The gentle raccoon is holding on that top spot, but just barely. It is close. Here comes our next question. It's a true and false. The air on Mars is 50 times thinner than on Earth. Is that true or is that false? The air on Mars is 50 times thinner than on Earth. A couple more seconds to get that answer in. All right, good job. It is 100 times thinner is what we learned today. Good job to all those who went out there with false. Captain Orcs slides into first. Let's go to our next question. This one is going to be another multiple choice. So the difference between a lander and a rover. A lander has wheels, a rover doesn't. A rover has feet and no wheels. A rover has wheels, a lander has feet, or there's no difference. That's a wordy one, so it might take you right down to the wire to get that correct answer in. All right, good job. A rover does have those wheels, and a lander is staying put with those feet. But I like the idea of one that can shoot a rocket back out into space. That's pretty awesome.
Yeah.
What did that do? Speedy Seal has been speedy. They've taken that third spot, but here's what it all comes down to. This final question. Where will the soil from Mars return to? Was it going to return to Utah, to California, to the ocean, or to Florida? Where is it going to re-enter? And where will it be picked up from? Utah, California, the ocean, or in Florida? All right, that is correct. It is Utah. Let's see what our podium looks like. We have third place, the Captain Orcs. The Gentle Raccoon in second. And no one could catch that Speedy Seal. They held on for that final victory. Good stuff. All right, crew, thanks for playing along with us. Let us jump into our Q&A action. We've got great classrooms. If you're tuning in on YouTube, use that chat sidebar and get some questions in there for us. But for now, why don't we start with a trip to Portugal first and Mr. Mark's crew. Let me bring them in live there. Hey, everyone, how are we doing today?
Fine, and you? Sorry, we had some internet problems, but I think now we're live.
It's looking good now, nice and clear. All right, who's got a question for us?
Becky. Okay, we have a question.
Hello.
Hi.
So I wanted to know how do you guys control the rovers that are in Mars with the late signal that you guys receive there?
That's a great question. Yeah, so the question is, how do we control the rovers? But there's this delay between when we send a signal and when the rover receives that signal. So this is tricky. We don't have a joystick where we say, go left, go right. What we do is the rover takes pictures and we say, oh, that's interesting. Let's go over there. So we're going to tell the rover, we want you to go to that point. And we might suggest a path, but the rover has some artificial intelligence where it says, oh, you know what? If I get to an obstacle, a rock that's in the way that maybe the people on Earth didn't know about, I'm smart enough to go around it. Or maybe the rover gets stuck and then it says, you know what? I'm actually confused what I should do. I'm not really sure. I'm just going to stay here. I'm going to send a signal back to Earth that says, hey, can you help me out? And then the people will help me out to get to that place. So it's a combination of we suggest a place, the rover will use its own intelligence to make the best possible decision on how to get there, And then it might ask us for help along the way.
All right. That's so cool. So many great uses for AI, and yeah, the robot kind of having that bit of freedom, but still being able to ask for help. I think that's really cool. Okay, well, let's jump to another classroom here. We are going to go to, let's see, Mr. Barr's crew is in Ontario, Canada, a grade 6 class, so they're definitely studying space this year. Let's bring them in front and center. Hey, everyone, how we doing?
Good. Glad to be here.
Awesome. All right, we're ready for you.
All right, I've got a question from our friend Ashton here. So Ashton, come on up.
How long were you in school for to be a rocket scientist?
Yeah. So after high school, I got my undergraduate degree from the University of Texas. I did it in aerospace engineering, although I'll say that it takes all types of engineers and scientists and business people to make a place like NASA or JPL work. My degree was in aerospace engineering. After that, I went to Georgia Tech, Georgia Institute of Technology in Atlanta for a master's degree. And then I came to JPL. So it took me 5 years for my undergraduate and 2 years for my graduate degree. A place like JPL, we have our workforce of engineers and scientists. About a third of them have bachelors, a third have masters, and a third have PhD. So it's pretty evenly split. I'll also mention, I didn't know I wanted to be an engineer. I wanted to be a doctor most of my life. And senior year of high school, I decided I didn't want to be a doctor, but I didn't know what I wanted to do. So then I went to college for business school. And I went to actually New York University. And I decided, oh, you know what? I miss math and science. And so then I thought about what uses a lot of math and science. And I grew up in Texas near Johnson Space Center, which is, Houston, we have a problem. This is where mission control for the astronauts are. And I said, you know what? That stuff is really cool. Maybe I want to be an astronaut. And so I looked up a lot of biographies of astronauts. And a lot of them did engineering. And I said, aerospace would be cool. So I transferred to University of Texas and did aerospace engineering and decided, you know what, designing spacecraft is really fun. And so from then on, it just took off for me and worked out.
All right. And, I love stories like that because there is no right or wrong way to get into science. There's no rule that says you have to know by your 10, 15, 26, 40. And there's no rule that says you can't change your mind if something excites you or you have a passion for something. So yeah, stories like that are awesome. And I mean, I think I would be accurate in saying that you love your job and you get to work with some pretty cool people.
I do. Yeah, it's exactly. The people is exactly what makes this place such an awesome place to work. I'll also say one more thing, Joe, that you reminded me of, which is after 8 years at JPL, I left JPL to do very different work. I was working to use my engineering background to design things to lift people out of poverty. And so I would travel to Africa and India and other places to design things, whether it was agricultural devices or other types of devices that helped people get out of poverty. And so that was really fulfilling, really fun, and a different way to use the same skill set that I have in engineering, which is designing something to solve a problem for a different application. And that was great too. And that was changing my mind in my 30s.
Yeah. Awesome. Very cool. That's the thing. Life is pretty exciting if you just kind of follow the twists and turns and go with it. Very cool. Pennsylvania, we'll take a trip to the US now. We have a crew there. I know that their microphone wasn't cooperating, but if they want to use this, well, let's try. There they are.
All right, get behind.
We've got microphone. There we go.
All right.
I was wondering, what's the timeline for everything that you have planned?
A lot of these missions take a long time. And so it's funny because it depends on the type of mission. Sometimes we write proposals for missions, which means NASA will say, we have this chunk of money. Anyone can tell us how they would use that money for exploration. And so we'll write a proposal, and maybe, if it got selected, then maybe depending on the size of the mission and where it's going, it might be, somewhere between 5 to 10 years before it's ready to launch. And depending where it's going, it takes a long time to get there. So going to Mars typically has taken us 6 to 9 months. This mission is taking a different route because it's so big and heavy that we have to take maybe a more fuel efficient route. So this one's going to take, I think, on the order of 2 to 3 years to get to Mars once it launches. When we go to places like Jupiter, that's even longer. It's 6, 7, 8 years to get to Jupiter because it's so far away. So it's funny because you might work on a mission and design it for like, let's say 5-ish years, then it launches and you're doing something else. And maybe you'll come back to it in 8 years when it's at Jupiter, or maybe you won't. And maybe it'll be a different group of people. But in the meantime, you're doing other really, really cool things. So yeah, these missions do take some time. I would say roughly 5 to 10 years per mission, from like the very beginning to getting somewhere or launching.
All right, great question. Let's go to our crew who are joining us in Mexico. Where are they? There they are. So it looks like some 7th graders. Let's bring them in front and center. Hey, everyone, how are we doing? This is a warmer hangout today. The last event they joined us for, they were connecting all the way up at Cambridge Bay in the Arctic, and it was a snowstorm.
Oh, wow.
Up there. There's everyone.
And you're muted right now.
All right. Yeah, grab that mic for us.
Hello,
Perfect.
everyone. Ravi. Manuel has a question for you.
What was the most difficult part of making the Rovi?
The most difficult part of...
Yeah, the most difficult part of making the rover, doing the rover.
The most difficult part of making the rover. That's a really good question, because there are so many things that can go wrong in any mission. And it's hard to say there's one most difficult thing. The part I can focus on or talk about is the part that I helped work on, which was on the Curiosity rover, the landing part. And on the landing part, what we do is we get in a room and we ask everyone, what are all the different things that can happen that would make it go wrong? And we just have this list that is so long. And then we think, which ones are the ones we're most worried about? And what can we do about it? And so it's hard to say there's any one thing, because, we did parachute testing where the parachute just ripped to shreds, and that became a big problem. In designing the wheels, while a wheel seems easy, a wheel on Mars that you can't fix is actually a very difficult thing. You can't send someone there to fix it. And so we had to reinvent the wheel in many ways. There's so many little things. The material. So we come in super hot, super fast on Mars, and all that speed causes us to get really hot, almost as hot as the surface of the sun. So material had to be invented in order to make sure that we wouldn't burn up. So while the outside is really hot, the inside is like room temperature for the spacecraft. And so there's so many challenges along the way. It's hard to really say just one. There were probably a million things that literally could have gone wrong that people had to design a solution for.
All right. That's a great question and a really great way to kind of put everything in perspective. I mean, all the engineering that went into it and all the new ideas and coming up with new ways to solve challenges that hadn't been encountered before. Yeah, pretty exciting environment to work in. Okay, we have to bring in Mr. Shattuck's crew joining us in Ontario.
What's up?
Hola.
All right, we're ready for you.
My name is Emily, and I want to know why, if you can parachute a rover down, how come you can't parachute a person down to Mars?
Such a good question. A rover down, why can't we parachute a person down? So a rover, this is the size of a car. If you send a person has to have some way to breathe, food, water, a habitat. You have to bring so much more stuff. And so instead of sending a car, you're almost sending like a small house. And the bigger stuff that you send, the harder it is. So remember, the air on Mars is really thin. So that's why, even though we have this parachute was 7 stories tall or wide, and it was just for a car. It turns out you can't just keep making parachutes bigger and bigger, because it's much harder to design a parachute that's big enough to land a small house. And so we have to invent a new way to land really heavy things on Mars. And so one of the challenges is, how do you land something that's much bigger than a car? And we're still trying to figure that out. It's something that we have to have a new creative way to figure out how we're going to do that. And so that's one of the challenges. Another challenge is, how are people going to survive on Mars? There's more radiation. Can you make water on Mars? Can you make oxygen on Mars? Can you do all these other things? Can you grow food on Mars? How do you keep people alive for a really long time on Mars? And so there's all these other challenges that we have to work out along the way.
All right. But we still have some time for some questions. So we're going to do a speed round and see how many we can squeeze in. So I'm going to mix up the order just to keep things happening here. I'm going to bring in our crew in Pennsylvania first and see if they have a follow-up question. Looks like you've got a rocket there as well in the background.
All right, what is it? Go.
What was your favorite part in like your job in making the rover?
Oh, I think Ravi might have froze on us. Let's give it a second and see if he comes back for us.
Try it again. Can you hear it now?
Oh, no. We've got you. I think Ravi froze on his end, his connection. Yeah, we've got you loud and clear.
Okay.
So we'll see if he can get back in. We might actually see him leave because that happens sometimes. You get kicked right out, and then he'll come back in and join. That'd be really impressive if he was just frozen there, just messing with us right now.
That would be.
Oh. There we go. We had you on double screen for a second there, but you're back.
Look, Veronica moves up to the upper right.
I know.
Yeah, no worries. Can you hear us okay?
I can hear you. Yeah.
Okay, perfect. Did you catch the question?
I did not hear the question.
Okay.
Sorry, my question was, what's your favorite part of your job and the favorite part of making the rovers?
Ooh, I love that question. The favorite part of my job is definitely the people I get to work with. I can have a question about anything, and the world's expert for that answer is probably down the hall. You just have this amazing brain power that's at NASA and JPL that you can just tap into. And the people here are here because they're excited about the work. And so they're all excited about, helping us solve this same problem together. And so that's what's really cool. Also, in addition to that, it's just the types of problems we solve. Very few places get to say we're looking for life on other planets, or that we're building spacecraft to explore a place that no one's ever been to. We are the next generation of explorers. And so that's really exciting. My favorite part about the rover mission is, I think the part that I get to work on, which is the landing part, is the most exciting part. It's so much has to happen in such a small amount of time. It takes us months and months and months to get to Mars. And when we're on the surface, we have years, the mission is years long. But for Mars, there's like a 7-minute span where hundreds of thousands of things are happening in a very small time frame and it all has to go right. And any one thing can cause the whole thing to fail. And so I think the exciting part is the rush and the adrenaline of watching that live happening and just making sure it all happened. The design process of, let me figure out all the things that can go wrong and try to solve all those problems.
All right, great question. And if you have time today after this event, go on YouTube and look up 7 Minutes of Terror, the landing of Curiosity, and you can kind of get a feel for how everybody was feeling and everything that had to happen in that short period of time. Okay, Mr. Drew.
When is the dirt tube from Perseverance supposed to land in Utah?
Good question. Let's see. So I think, if we launch in about 5 years, it'll take about 3 years to get there. And I think about a year later we launch. That's like 9 years. And then the return trip, I forget exactly how long it is. So let's call it in about 10 to 12-ish years, we would have those tubes of dirt in Utah. And it sounds like a long time, and it is. And it's funny. We're people just like you, and we think, oh man, that's so long. But it's just the nature of the business of, we can't change where the planets are. It takes a certain amount of time to get there, and we have some constraints that we have to work with. And we want to make sure that we build the best possible spacecraft we can for the highest chances of success. These things aren't easy. Landing on Mars, even though the last many times we've done it successfully, we have failed many times also. And so we try to learn from our mistakes. Every time we go, we're on the edge of our seats, and just hoping. It's a lot of work, but there's also an element of luck in making sure that we can't think of everything that can go wrong, and we need a bit of luck to make sure that it all goes right. And so these things unfortunately take time, but we'll see.
All right, well worth waiting for, and there's large sums of money involved too. So yeah. All right, Mexico, let's bring you back in.
Is out loud.
Okay. What's the most shocking thing that you discovered in space?
Ooh, the most shocking thing we've discovered in space. Oh, that's a tough one. I'm going to answer maybe a slightly different question, which is, I think the most amazing thing about space, which is that, we've learned that we are made of the same things that stars are made out of. And so isn't that really cool? Like, we think, so you might have heard of the Big Bang, where, from nothing, just this big explosion. And as things were cooling or whatever happened, elements like metals and everything started forming, gases started forming. And those are the same materials that we are made out of. So as stars exploded, Big Bang happens, stars form, stars explode, and all these metals go out into the universe. Those are the things that created life on Earth. And if there's life out there outside of Earth, those are the same things that created that life as well. And so you are made of stardust. You are made of the things that stars are made out of. And that's really amazing to me.
All right. Very, very cool. A good choice. Absolutely. Okay, let's jump across the Atlantic and see if there's another question there for us.
Samuel.
What will you guys do if the robot broke?
What do you do if rover broke?
Rover?
Oh, what do we do if the rover breaks? I love this question. So we cannot send a mechanic. We can't send someone to fix it. What we do is we get creative. We say, well, which part broke and how can we work around that? So for example, we had these twin rovers, the Spirit and Opportunity, and they were the size of your student desk. And their wheels started breaking. And we said, okay, well, there's 6 wheels. Let's keep going with the 5 other wheels. And then another wheel breaks. And we say, okay, well, or maybe it actually got stuck in some soil. We said, okay, well, what can we do if it's stuck in the soil? So we had people think of ideas, and maybe we can go backwards and maybe come out of the mud that way. Not mud, the dirt. Maybe we can use the robotic arm and push down on the soil, and maybe that'll lift the leg up. And we just come up with creative ideas on how we can solve that problem. And sure enough, one of those solutions worked, and it's driving again. But then more wheels break and more wheels break. And then all of a sudden we say, so many wheels have broken that it can't drive anymore, but maybe now it's a lander, and maybe now it's just going to do science from where it is. And so we do that. But then it starts losing more power and other things go wrong. And at some point, you say, okay, you know what? It's been a good run. Maybe that's it for this rover, and let's focus our energies on other stuff. So we, depending on the problem, we try to come up with a creative solution to work around that problem. And at some point, maybe it's just it's been a good ride.
All right, great question. Final question goes to Mr. Barr's crew. Great 6s.
All right, we have our friend Declan coming up. Come on up, Declan.
If you could land a rover on another planet other than Mars, what would it be?
Ooh, that's a good one. I would go. I'm torn between going to Europa, which is an icy moon of Jupiter. That's a really cool one because we think under miles and miles of ice is a liquid water ocean. And we know from Earth, when there's water, there's life. And so I would love to have a rover driving around, have some way of like drilling through the ice and getting like a submarine to go in the ocean and looking for like, do we see any life? Do we see maybe huge ocean monsters? Do we see small things? Do we see anything at all? The other thing I'm wondering about is Titan. Titan is a moon of Saturn, and Titan has a lot of it has methane gas, and methane is a type of carbon. So that's another place, we on Earth we say anytime we see life, we see carbon, and maybe Titan has some sort of life. So we're actually sending, NASA is sending with the Applied Physics Lab, APL, sounds like JPL, but it's APL. They're sending a quadcopter to Titan to help understand what Titan is like. And we think there's maybe liquid oceans of methane. There's lots of mountains. Titan's really cool because it has a lot less gravity than Earth, but it's really thick atmosphere. So if you were to run really fast and have like big planks on your hands and flap your arms, you might actually be able to fly on Titan. Isn't that cool? So I would maybe send a rover there too, just because it's a cool planet. A moon. Close enough.
Awesome. Thank you.
Yeah.
All right. Well, Ravi, I think we've got to start off with a huge shout out to our classes today, a real international group spreading out. Thank you for all of those amazing questions. playing along the Kahoot. It's always great to have you with us. And then a huge shout out to you and everybody at JPL. Everyone's doing incredible work. We're learning so much about our solar system. We're learning so much about our planet. And, we love having you join us. Thank you so much for being so generous with your time and sharing all the cool things happening.
Thank you. I love it. This is so much fun. Thanks for all your questions. And yeah, like you said, thanks to all the students for tuning in.
All right. Well, those classrooms with us, I'm going to turn bring it back in. Let's get nice and loud. Say goodbye and thank you. All right. Have a great rest of the day, everyone. A great rest of the week. Thanks so much for being with us.
Thanks. Bye, everyone.